This presentation is on the normal distribution. We will learn what the normal distribution looks like, why it is important in statistical analysis, and how to understand what the normal distribution is telling us via z-scores. First, we examine the shape of the normal distribution. At this point, you should have your Pollock 1 textbook open to page 139 for a good picture of the normal distribution. It looks like a bell curve, and in fact, it's often referred to by that phrase. Think of the horizontal line that's at the bottom of the normal curve as values of a variable that we will call x. And think of an imaginary vertical axis on the left-hand side of the drawing as a measure of the frequency of occurrence of the variable values in an array of data. We will need to think of the variable values in a special way, however. To do that, let us first be even more specific in our demarcations of the x-axis. Let us think about the measure of central tendency that we have covered in a previous presentation. The mean, median, and mode are good measures of central tendency and are appropriate depending on the level of measurement of the variable. For our purposes, the mean, median, and mode all coalesce around the value of z equals 0. What is z? A z-score is defined as the observed value minus the mean value divided by the variable's standard deviation. Thus, if an observed value is exactly the same as its mean, then the z-score for that observation is 0. If the z-score is 1, then that observation is exactly one standard deviation unit above the mean value. If the z-score is -1, then that observation is exactly one standard deviation unit below the mean value. So what? The utility of z-scores is that we can represent each value of a variable as a standardized score. We can thus interpret the extent to which a value is an outlier observation, or far removed from the other observations in an array of data. Z-scores that are close to 0 are not outliers, while z-scores farther away from 0 are increasingly outliers. Z-scores also allow us to draw a picture of a normal distribution. We're fortunate that there are many variables that are described in a normal fashion. Also, we can use the central limit theorem if we have enough observations. The central limit theorem says that if the number of observations of a variable is equal to or greater than 30, we can then assume that the sample distribution looks normal. We can further use the empirical rule to understand just what percentage of observations in a sample of data lay within certain standard deviation units of the mean value. We start with 34% of all observations lying between a z-score of -1 and 0, and 34% of all observations lie between a z-score of 0 and 1. Thus, 68% of all observations are between a z-score of -1 to +1, or a little above 2/3. Nearly all observations, or 95%, are between z-scores of -2 to +2, and 99% of all observations are between z-scores of -3 to +3. Hence, if you calculate a z-score less than -3 or greater than +3, that is an exceedingly rare observation, either extremely high or extremely low. We have thus been introduced to the concept of the normal distribution.